Welcome back, everybody, for another deep dive. This time, we're going into machine learning, specifically how researchers are improving on a pretty powerful type of AI called, RNNs, recurrent neural networks.
Right.
You sent over a research paper,
Yes.
and the title is Trajectory Flow Matching with Applications to Clinical Time Series Modeling.
Okay.
And you really want to understand, why this new method is called trajectory flow matching, or TFM for short.
Okay.
Why it might be better than these RNNs for analyzing things like patient health data.
Yeah.
And I got to say, this paper gets pretty dense.
It's true.
But luckily, we have our expert here to help us unpack all this.
Of course.
Break it down into, kind of the most useful insights.
Absolutely.
So clinical time series data. This is stuff like, a patient's heart rate over time.
Right.
Blood pressure, things like that.
Yeah, exactly.
It's not the easiest data to work with.
No, it's definitely challenging.
So can you kind of just set the scene for us? What makes it so tricky?
Well, it's tricky because it's what we call stochastic.
Stochastic.
Yeah, it means there's randomness in how it evolves.
Okay.
And it's also irregularly sampled.
Okay.
So the measurements aren't taken at fixed intervals. If you think about taking a patient's temperature every hour versus maybe they come in for a checkup once a month.
Right.
That makes it really hard for traditional methods to really capture those nuances.
Yeah, it's not like you have these neat data points on a graph, right?
Exactly.
It's more like trying to piece together a story from a bunch of jumbled notes. And I noticed that this paper talks about something called neural stochastic differential equations.
Yes.
Neural SDEs.
SDEs.
What are those?
Yeah, so neural SDEs,
Right.
they're this relatively new type of model that's actually really well suited for representing these complex systems
Got it.
that change over time,
Okay.
like a patient's health.
Okay.
Think of it like trying to understand how a leaf flows down a river.
Okay.
You're trying to map the currents in the river.
To see how the leaf might go downstream.
I like that analogy.
Yeah, so neural SDEs, they attempt to model the underlying dynamics of a system.
Okay.
But traditionally, the way that we train these SDEs is a bit of a pain.
Really?
Yeah, we use this process called backpropagation.
Okay.
And it involves going back through all the calculations and adjusting the model's parameters.
Okay.
And it can be really unstable, especially with SDEs.
Unstable in what way?
Well, imagine trying to retrace your steps in a dense forest. You might get lost along the way, right?
Yeah, for sure.
And with backpropagation, that can happen.
Huh.
It can be computationally expensive. It can take a lot of time.
So it's like this computationally intensive process, and on top of that, it can be unreliable.
Right.
So is that where TFM comes in?
Yes, exactly.
Okay, so tell me, how does TFM address these issues?
Well, TFM takes a completely different approach.
Okay.
And it's a really elegant one, I think. It's called a simulation-free method.
Simulation-free. So instead of backpropagating through that entire SDE, TFM focuses on just matching the flow of trajectories at different points in time.
So the trajectory is like the path of that metaphorical leaf in the river.
Precisely.
Okay.
It's like we're trying to figure out the river's currents by looking at where multiple leaves are at different times without needing to simulate the entire flow.
Okay, so it's cutting through the complexity
Yeah.
and focusing on those essential relationships between those snapshots in time.
Exactly.
I can see why this could be a big deal for clinical data,
Right.
especially because it's so irregular.
Yes, definitely.
It's not neatly spaced out,
Nope,
like you said.
not at all.
So TFM is faster.
Yeah.
It's more stable.
more stable.
And it seems like it's maybe more suited to this messy kind of data that we see in the real world.
Precisely.
So are there any other advantages that TFM has?
Yes, actually there are.
Okay, I'm all ears.
There's one key advantage that the paper really highlights, and that's called coupling preservation.
Coupling preservation.
Yes.
What is that?
So imagine you're looking at a patient's heart rate and their blood pressure over time.
Okay.
Coupling basically means recognizing how changes in one of those variables might directly influence the other.
Oh, yeah.
So if the heart rate goes up, how does that affect the blood pressure?
Right.
TFM is really good at preserving these relationships.
Okay.
And it gives us a much more holistic view of the patient's health dynamics.
Right. So it's not just looking at these isolated data points.
Exactly.
It's actually trying to understand how they relate to each other
Precisely.
and how those relationships change over time.
Yes.
That's super important.
It is.
Especially in healthcare, where These systems are all interconnected.
Absolutely.
So we've got faster, we've got more stable, we've got these crucial relationships.
Mm-hmm.
What else? I'm seeing here in the paper something about uncertainty prediction.
Yeah.
What is that all about?
This is one of the really exciting things about TFM. It doesn't just give you a prediction.
Okay.
It also tells you how confident it is in that prediction.
Wow.
So, think of it like the AI saying, I'm 90% sure this is what's going to happen.
Right.
Or, take this with a grain of salt. I'm not really sure about this one.
So it's giving you a sense of how much to trust that prediction.
Exactly.
That's incredibly valuable in healthcare.
It really is.
Especially when a doctor needs to make a decision based on that information.
Absolutely.
So it's like adding a whole layer of nuance that's often missing from AI predictions.
I agree.
It's not just a yes or no. It's like, well, I'm kind of leaning this way, but I'm not 100% sure.
Exactly.
That's a game changer.
Yeah.
So this all sounds fantastic in theory.
Right.
But did the researchers actually put TFM to the test?
They did, yeah.
Did they test it out on some real data?
They did.
Okay, so let's get into the nitty-gritty.
Let's do it.
How did it perform in the real world?
Well, they tested it out on several real clinical data sets, focusing on patients with conditions like sepsis, cardiac arrest, and gastrointestinal bleeding.
So some pretty serious stuff.
Yeah, definitely.
And what did they find?
Well, the results were really impressive.
Impressive in what way?
TFM consistently outperformed other approaches
Oh,
by a lot.
So, what are we talking? How much better?
Well, it really depended on the data set,
Yeah.
but they saw reductions in prediction errors anywhere from 15% to 83%.
Wow, 83%, that's huge.
It is.
That's a massive improvement.
Yeah, and don't forget about that uncertainty prediction we talked about.
Right.
TFM delivered on that too.
So it was giving accurate uncertainty estimates along with its predictions.
Exactly.
Wow, this is starting to sound like it could really revolutionize how we analyze patient data.
Yeah, it has that potential.
So in the outline you sent over, you mentioned a bigger picture beyond healthcare.
Yes.
Could you expand on that a bit?
Sure. So what's really exciting about TFM is that it's not limited to just clinical applications. This method has the potential to be used in any complex system where understanding how things change over time is critical.
So give me some examples. What else could we use this for?
Well, think about financial markets.
Okay.
Stock prices constantly fluctuating, influenced by all sorts of economic factors.
Right.
Or weather forecasting.
Okay.
You've got these huge amounts of data trying to predict these super complex atmospheric systems.
Yeah, it's all about understanding how things change.
Exactly. It's about understanding the dynamics of change.
And how those changes relate to each other.
Exactly.
It sounds like TFM could be a really powerful way to make sense of all of that.
I think so.
So the researchers highlight this potential in the paper.
Yes.
And they point out that TFM's ability to preserve coupling makes it particularly well suited for tasks like causal inference.
Right, because you're trying to understand those relationships between the variables.
Causal inference, that's a fascinating area.
It is.
It's not just about seeing that two things are correlated.
Yeah.
It's about trying to figure out what's actually causing what.
Exactly, which is really difficult.
Especially in healthcare.
Especially in healthcare.
Where there are so many intertwined factors.
Absolutely.
But it sounds like TFM's approach could open up some new doors.
I think so, because it's focusing on how those relationships evolve over time.
It's like we're moving beyond just making predictions. And we're starting to delve deeper into the why behind the data.
I agree.
So let's talk about those potential implications for healthcare.
Sure.
What could TFM actually mean for the future of how we diagnose and treat patients?
Well, the researchers point to a few really key areas.
Okay.
First, there's the potential for earlier and more accurate diagnoses. By capturing those subtle changes in a patient's data over time, TFM might be able to detect warning signs that traditional methods would miss.
It's like being able to see the storm brewing before the rain even starts.
Exactly.
It's not just looking at a snapshot.
Right.
It's seeing the whole trajectory.
Yes.
And that's so important.
It is.
Especially for conditions where early detection is critical.
Absolutely, because early intervention often leads to better outcomes.
Exactly.
So that's one key area.
Okay, what else? What other potential impacts did they highlight?
Well, they also talked about the potential for more personalized treatments.
Okay.
So TFM could help us understand how individual patients might respond differently to various therapies.
Interesting.
You can imagine using TFM to actually model a patient's unique health dynamics.
Right.
And then using that model to predict which treatment path would be most effective.
It's like tailoring the treatment to the individual.
Exactly.
That's amazing.
It's about moving away from this one-size-fits-all approach.
Right.
And moving towards personalized healthcare.
Guided by a deeper understanding of each person's individual variability.
Exactly.
That's really powerful.
It is, and the researchers believe this could lead to better patient outcomes overall.
So fewer misdiagnoses, more targeted treatments, and a more proactive approach to healthcare.
Precisely.
It sounds like a pretty good future.
I think so.
But I imagine there are also challenges and risks to consider as this technology evolves.
Of course, the researchers acknowledge that TFM is still in its early stages.
Right.
More research is needed.
Of course.
To really explore its full capabilities and address any limitations.
So what kind of limitations, what should we be keeping an eye on as this technology develops?
Well, one thing they highlighted is the importance of data quality.
Okay.
And representativeness. Like any machine learning model, TFM is only as good as the data it's trained on.
Right. So if the data is biased or flawed, those flaws could be reflected in the model's predictions.
Exactly. So we need to be very careful to ensure that the data used to train these models is representative of the diverse populations that they're meant to serve.
That makes sense. What else?
They also brought up the challenge of interpretability. Right now, TFM, like a lot of deep learning models, can feel a bit like a black box.
A black box.
Yeah.
Wow.
It can make these really impressive predictions, but it's not always clear how it arrives at those conclusions.
So we get the insights.
Right.
But we don't really understand the reasoning behind them.
That's right.
It's like having this brilliant but mysterious oracle.
Exactly.
And in healthcare, that lack of transparency can be a problem.
It can, because doctors and patients, they want to understand the basis for decisions.
Especially when those decisions could have a real impact on someone's health.
Absolutely.
So interpretability is a big one.
Yes, and the researchers really emphasized the need for more research in this area.
So trying to find ways to make these models more transparent.
To make them more understandable and accountable.
So it's not just about power, it's also about trust.
Exactly.
And making sure that these AI tools are used responsibly.
I agree.
So they stress the importance of rigorous validation in real-world settings. So not just testing it out in a lab, but actually seeing how it performs in a real hospital.
Exactly, because before TFM can be widely adopted, it needs to be rigorously tested. In
those real-world scenarios.
To make sure that it's actually reliable and improves patient care.
Right. And even after it's deployed, we need to keep monitoring it.
Yes, absolutely.
To make sure it's still working as intended.
Ongoing monitoring and evaluation are crucial.
It's not just set it and forget it.
Right.
These AI tools need to be constantly assessed, adjusted,
and refined
to make sure they're delivering on their promise.
Exactly.
So this has been a really fascinating deep dive into TFM.
It has.
We've covered so
much.
From the technical details to the broader implications and the ethical considerations that we need to be thinking about.
For sure.
But I want to bring it back to you, the listener.
Okay.
What are your thoughts on all of this? What stands out to you from all this information about AI in healthcare?
Well, I think what's really exciting is this potential shift from reactive to proactive healthcare.
Oh, interesting.
So instead of waiting for diseases to develop, we could use these tools to predict and prevent health problems before they even arise.
That's a really interesting idea.
Yeah.
So could we actually use TFM to predict individual health risks?
Potentially, yeah.
So people could take preventative measures.
Exactly.
It's like getting a glimpse into your health future and then having the power to change it.
It's a powerful concept.
It is.
As these models get more sophisticated and we gather more data, we could potentially use TFM to identify who's at higher risk for certain conditions.
And then instead of waiting for symptoms, you could get personalized recommendations based on your own unique health trajectory.
Exactly.
Maybe it's lifestyle changes or early screenings or even tailored medical interventions.
Absolutely.
That's powerful stuff.
It is.
It's like empowering people to take control of their own health.
I agree.
But of course, we have to be mindful of the ethical considerations.
Oh, absolutely.
We have to make sure this information is used responsibly.
Right.
You know, protecting privacy, preventing discrimination, and ensuring that people understand the limitations of these predictions.
Those are all crucial considerations.
Yeah, responsible development and deployment are key here.
For sure.
But if we can navigate those challenges thoughtfully, potential benefits are huge.
Enormous.
This has been a really incredible deep dive into TFM.
It has.
We've learned so much.
Yeah, it's a fascinating area.
From the technical stuff to the broader implications
Mm-hmm.
and the ethical things we need to keep in mind.
It's important to consider all of those aspects.
Absolutely.
But I think it's clear that TFM represents a remarkable advancement in AI.
It really does.
And I think we're just scratching the surface of what it can achieve.
So as we wrap up, I want to leave you, the listener, with one final thought.
Okay.
We've talked about predicting trajectories,
Mm-hmm.
understanding relationships,
Mm-hmm.
and even the possibility of personalized preventative care.
Yeah.
But what if we take this a step further?
Okay.
What if TFM and these other AI tools
Yeah.
could help us not just predict the future,
Okay.
but actually shape it?
Wow, that's a powerful idea.
So if we can really deeply understand these complex systems,
Mm-hmm.
can we then use that knowledge to nudge those systems in a more positive direction?
Minus the hope, right?
Could we create a healthier future?
Yeah.
Not just for individuals,
Mhm.
but for entire populations.
It's an exciting possibility.
It is.
And I think TFM is just one example of how human ingenuity can be harnessed to create these powerful tools.
Absolutely.
The future of AI is full of possibilities.
It really is.
And it's up to us to shape that future responsibly.
Well said. That's a great note to end on.
Yeah.
Thank you so much for joining us on this deep dive.
It was my pleasure.
We'll see you next time for another fascinating exploration of cutting-edge ideas.